this video, I want to talk about two special cases that we need to think about when it comes to particle motion. And mostly these special cases are relatively simple, but they are useful because they can sometimes simplify our analysis of particle motion and how we look at it. So the first special case that I want to talk about is when we have a known or constant velocity. So the object is moving along at a single speed, a constant velocity, and there's no change to it in that situation. Now, constant velocity, of course, implies that acceleration must be zero, right? By definition, if the velocity is going to be constant, then the acceleration has to be zero. So that's one tiny bit of information that is useful to us. And then we want to think about, well, what does it mean for the position, and how do we use that? Well, we know that from velocity, we can integrate to get to position, right? So writing that out, we know that position, which I'm going to call x as a function of time, is equal to the integral of v with respect to time, right? So we have this integration, and we can go ahead and carry out the integration. And v being a constant, we would just pull that outside the integrator. Then we're taking the integral of dt, and we end up with vt, right? But if we're treating this as an indefinite integral, then we have this constant of integration, which we would sometimes write as c, right? And in order to get rid of c, we need to know something about our situation, right? So I can bring this x of t down. And the thing that we can assume that we might know is what the initial position of x is. Now, the initial position of x would be the position, or the solution for x when t is 0. So if I say t, let's pretend that this is equal to 0, and then of course t over here is equal to 0 as well, we would say x of 0 is equal to c. So then we'll go ahead and define that as x naught. And all that means is it's the initial position of x with respect to time when time is 0. So if I want to write this out, then I can say my function for position x of t is equal to vt plus x naught. So all that means is it's velocity, my constant velocity, times time, plus whatever my initial position is. And this should kind of make sense from what we've talked about before when we introduced 1D particle dynamics, is that, or kinematics, is that if we have a particle moving from one point to another, starting say at time t equals 0 to some new time t, we would have some x equals x naught, and our new x over here is equal to x naught plus whatever x is changed by, right? So this initial x naught is the thing that we're adding on there to get this function for x. So that can be useful in that it gives us an equation under the constant velocity condition for the position. And again, we know that in that condition, acceleration is also 0. The next condition that we would want to look at is constant acceleration. So constant acceleration works in basically the exact same way, and it's a pretty common condition, right? Because anytime we have gravity, that would be a constant acceleration. We could have a constant acceleration of a vehicle, like a car. All of those things are pretty common scenarios that we might encounter. So if we define the acceleration as a constant, we can work our way backwards then to velocity and to position. So we'll do that in the exact same way. We know that velocity is defined as the time derivative or excuse me, time integral of acceleration. Acceleration being a constant, we can pull that out, and taking the integration of dt, we get at, right? And so we have velocity equals acceleration times time. Again, we could have this constant of integration that we add on, but we're going to treat it in the exact same way that we did up here and say that if we define the initial velocity as v naught, then that becomes our constant of acceleration. Now there's another way that I could express this. I could treat this as a definite integral, in that I could integrate from t equals 0 to some time t, and I would get the same thing, but I'd have to, again, know what that velocity is at 0, and that's, again, what I'm defining as v naught. Great. So we have this expression now, v equals acceleration times time plus whatever my initial velocity is. And that's going to be a useful equation. Next, I want to move up the chain one more step and get to position. So to do that, I know that my position x is equal to the integral of v with respect to time. And in this case, it's a little bit different in that v is not a constant, right? We just defined v to be a function of t. So if I plug my equation in here for v, so take this, plug it in for v there, I can take that integral, and I know that I'm going to integrate at. Well, let's just write it out. At plus v naught. V naught is a constant, and all of this with respect to time. The integral of at is going to be 1/2 at squared. The integral of v naught is going to be v naught t, where that is just a constant, v naught again. And my constant of integration, just like it did in the constant velocity scenario, becomes x naught. So now I have an expression that's really useful, and I can define that as 1/2 at squared plus v naught t plus x naught under constant acceleration. Now, there is another scenario related to constant acceleration that's pretty useful. You may recall that in a previous video we defined or created another definition for acceleration in terms of only the velocity and the position, and that was that the acceleration is equal to velocity times dv by dx. And we can look at this in the exact same way under this constant acceleration condition. So what I'm going to do to evaluate this and get it in a more usable form is separate my variables. So I'm going to take v and dv and put those together, and a and dx. And the reason I'm putting a with dx is because it's a constant, so it doesn't really influence the dx too much. And if I integrate both sides of this, I'm going to give it a definite integral, some definite integral limits from v naught to v on the left, and from x naught to x on the right. So first, on the left-hand side, the integration of v with respect to v is going to be 1/2 v squared. This will need to be evaluated from v naught to v. On the right-hand side, a is a constant, so I can pull that out, and I'm left with then ax evaluated from x naught to x. So if I substitute in these limits of the integration, I get 1/2 times v squared minus v naught squared, and set that equal to acceleration times x minus x naught. So if I do some rearranging, I can set v squared equal to v naught squared plus 2a delta x. So what I end up with, again, is a function that doesn't include time. I can solve for my final velocity if I know my initial velocity, my acceleration, which is a constant, and whatever change in position I've observed. So under this constant acceleration condition, I get three equations that are particularly useful to me. I get v of t equals v naught plus at. I get x of t equals x naught plus v naught t plus 1/2 at squared. And I get v squared, let's keep it consistent, we'll call it v of t squared equals v naught squared plus 2a delta x. And these three equations become useful for me under this constant acceleration condition, and we'll find that they are particularly useful when it comes to evaluating problems. All right, thanks.